I think we only really had time to talk how these hybrids look like. There was not enough time to talk about these hybrids, but you see, in this case, you have S plus P gives you two hybridized orbital. Here S plus P gives you three hybridized orbitals. And in the case of sp3, you have four hybridized orbitals. How the molecule looked like. It happens on the central atom. In this case, this central atom has one orbital pointing one direction. This is the hybridized orbital. And has the other orbital pointing the other direction. Again, orbitals like orbitals, one of them has a plus sign, other one part has a minus. Similar thing happened for this one, plus, minus. sp2 hybridization happens when you have three orbitals. One of them looks like that. Other one like that. And there is one more. And again, one has plus sign, minus, plus, minus. To imagine how the sp3 orbitals look like, first you have to understand that sp,p,p gives you four orbitals. To arrange them, here the arrange was on the line. And I show the line on the line, and the line is of course here. Here the arrangement is on the plane, and the plane of course is this plane. In the case of four orbitals, the arrangement is in space. And to imagine this, here you have the central atom. Here is one of the directions in the space. Here is another direction in the space. And now, to write the other one of them will be pointing here, and the other one will be pointing inside. This is difficult to draw, but it's very important that we know that if I write something like that, it's pointing outside. And when I write something like that, it's pointing behind. Okay? Just remember this. So you have these four directions, and now we can write the four orbitals. First one, of course, is pointing here. Second one is pointing here. Next one is pointing here. And the last one that we cannot see because it's behind, is pointing there. and only this part is sticking out. Now, important thing to remember is the angle here between these two orbitals is 180 degrees. The angle here between these two orbitals is 120 degrees. And the angle here between two orbitals is 109 point some small value of degrees. I think 109.8 or something like that. So next important thing. This means that these two atoms that are coming will be far from each other. Here they will be already closer to each other, and here they will be even closer to each other, which makes sense. Because if you have only two atoms, they take small part of the space. Three atoms already takes larger, and four of them even larger. You can ask me, is it everything? And the answer, of course, is not. You already used S. You used SP, SP2, SP3. What can be farther? You can try to use d orbitals inside. And there is hybridization d sp3. And for this one, of course, you are getting 5 hybridized orbitals. How does this look like? Turns out that it's not so different. Here they were on the line, here they're on the plane. In the case of 5 orbitals, one of them, okay, here is the central atom. One of them is up, another one is down, another one is here, another one is here, and another one is there. And like always, they look the same. So I just plot them very fast with the same color already. You see that with the same color, it doesn't look so clear anymore. Probably the last hybridization that you have to remember is the hybridization D2sp3, which would be 2d plus s plus 3p orbitals. And this one gives you 6 of them. And this one will look like that. We have the central atom in the middle, one of them at the bottom, one of them at the top. One of them sticking this direction, one of them sticking this direction, one of them behind, and one of them behind. What is the angle here? You see that it goes to 90 degrees, any two axes. So it's getting smaller and smaller and smaller. What about this one? Here is a bit difficult. Clearly this angle is 90 degrees. And clearly this angle is 120 degrees. So it's not very symmetric formula. I think there is only one molecule, well, maybe more, but one I can remember about, having hybridization D3sp3, having 3 d orbitals plus s plus 3p, and that gives you 7 molecular orbitals. But I mean, there is no much philosophy about this, because the 7 virtually would look the same like these two, means central atom in the middle, one up, one down, one here. Now one of them here, one of them behind, one of them behind here, one of them here. So again, this angle would be 90 degrees, but this angle would be as small as 360 divided by 5, 72, right? 72 degrees. And the molecule is IF7. Very strange molecule. Maybe there are some more, but I just know this one. And of course, if I really want, I can write the molecular orbitals everywhere. But this is not making the picture much more clear. 1, 2, especially in this case. Good. Now, why this is important? Because this one tells you that the number of neighbors also defines the shape of the molecule. So for example, when you have a structure CH4, then there is not much long thinking. You already know that there must be this structure. But surprisingly, there are molecules, NH3, that also have this shape. Why? It has only 3 hydrogen, 1, 2, 3. What about this one? Yes, there is 2 electrons from the nitrogen, lone pair that already has 2 electrons and is happy. It doesn't want to make bond. It can make a bond when extra H plus is coming. H plus is missing electron. So H plus can attach here, making the NH4 plus molecule that has exactly the same structure like this. Okay, so to define which structure it is and how many lone pairs we have in a molecule, we need some more material, and we do it probably in the next class. For today, I only wanted to show you that the hybridization defines you the shape of the molecule. The molecule can be linear, the molecule can be flat, the molecule can have the tetrahedral structure. Why? This is another important thing, to plot the shape of the molecule. In this case, the shape of the molecule will look like that, with the central atom inside. In this case, the shape of the molecule will look something like that. With the central atom inside. In this case, of course, there would be so-called here you just have, let me make some space on the blackboard. Here you have just the molecule in the shades of the triangle. In this case, you have a molecule in the shape of the tetrahedron. Now, easy to remember, tetra means 4 in Greek. Edr means corner. So 4 corners, 1, 2, 3, 4. Now this one is a strange shape. If you look at this one a bit longer, you see that this one consists of 2 identical figures. One, and then another one is at the bottom, looking exactly the same. And this one looks like a pyramid. So it's called trigonal bipyramid. You know what a pyramid is? It's in the Egypt, old Egypt. They have the shape like that. I don't know how to say in Chinese. Okay. So bipyramid, there are 2 of them. This one looks like people usually call it tetragonal. Tetragonal bipyramid. But the usual name for this is octaedr. So usually we are going to use this name. So again, octa means 8 and edr means the wall. 1, 2, 3, 4, 5, 6, 7, 8. Similarly, like here, tetraed means 4 walls. And this one, of course, would be pentagonal bipyramid. How do we write the energy diagram? You remember before we were defining that when we have, like, for example, oxygen atom and another oxygen atom, you can make that O2 molecule. And we said that we are starting with 1s, then we have the 2s orbitals, then we have the 2p orbitals, and the same for the other oxygen atom. We have the 2p, we have the 2s, and we have 1s. In the atom. And now in the molecule, 1s and 2s will make the sigma and sigma antibonding orbitals. Sigma and sigma antibonding. 2s and 2s, oxygen would be a linear molecule, right? 2 atoms must be on the line. So first, one of the s and one of the p make the 2 levels of the sp hybridization. They mix. And the other, there were 3 orbitals here and 1 here. Other 2 are going to the same level. There will be just the px and the py orbital. Similar things happen on the other side. One of the s orbitals and one of the p orbitals are making 2 sp hybrids. and the other orbitals, px and py, are here. So the orange line is just showing what kind of hybridization is happening. So before really making atoms, making molecule. Now we have the molecule. Then you know that the one S going to both of them with the linear combination plus and minus, making these two. Now the sp hybrids look like that. Two of them will have the sigma symmetry. So they make 2 sigma and 2 sigma antibonding. That will look like sigma, another sigma antibonding. Sigma and sigma, and here is sigma, sigma antibonding. Sorry, another sigma. Here is the sigma antibonding and sigma antibonding. Now, these two, they make pi orbitals and pi antibonding orbitals. Wrong. This one goes here, of course. And this one goes here. This one comes here. Okay. And that would be the end of the story, except that this story is wrong. Namely, S and P can make a hybrid only if S and P energy is very close. Unfortunately for oxygen, N and SP is very far, and they cannot make hybridization. So the real picture looks a bit different. I just showed you this to show that always using hybridization thinking can give you problems. For example, making such a false plot. In this case, the difference between 2s and p doesn't allow for making hybrid orbitals. So what really happens in this situation is, as I'm drawing now, you don't have the hybridization step. And the 2s and 2s, they are making sigma and sigma antibonding. Similarly, 2p orbitals, they are making the sigma, pi antibonding and sigma antibonding orbitals. Now I connect them. So one connection I already have. One, another one, another one, another one. Okay. Now one oxygen atom has 6 electrons. And another one has 6 electrons too. Okay, 6 or 8? Sorry, 8 electrons. Now I have to put these 8 electrons plus 8, total number 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16, once again. 2, 4, 6, 8, 10, 12, 14, 15, 16. Now, with the orbitals that are doubly taken, one of them has spin up, one of them has spin down. What about these two? How do you think? One up, one down, or both of them up? Both of them up. Okay, let's make a test. Up. Everybody's up. Turns out to be almost true. The possibilities are one possibility, second possibility, third possibility. One possibility of them up. Another one of them like that, and the another possibility is now turns out that this possibility and this possibility are not symmetric enough. So you have to consider also this version and also this version. Right? Now you have like all of them. Now, of course, with the plus sign and with the plus sign. Linear combinations. So it turns out this one is the lowest in energy. Turns out this one is a bit higher in energy. And turns out that this one is the next one in energy. So what happens for the oxygen 2 molecule? We know that the potential energy curve looks like something like that. Okay? And that would be this one. Ground state. I denote it by X. Usually in spectroscopy is denoted by X. Then you see that this one will spin up, and this one will spin up, spin down. The only difference is that one spin is down. It means the energy difference between them wouldn't be very big. And that's true. I denote this situation by A. And it turns out that the A state looks like that. Very close. And of course there is also the another one possibility that I denote as B. And the B one is a bit higher, but again very close. So again, you have to remember that electronic configuration like that is not good enough description even for molecules. One electronic configuration of single electrons can give you 3 different electronic states and 3 different curves in the real plot. But this is a bit complicated topic. You just remember that when I write that oxygen molecule, O2 is helium, I described this one already, then is sigma 2s2, sigma 2s antibonding 2, then is sigma 2p 2, then is pi 2p4, then it is pi antibonding 2, that this description is not everything. This one still doesn't tell you how these 2 electrons are put into these 2 orbitals. And we just wrote all the possibilities like that, plus plus, plus minus, minus plus, and both of them on the same orbital. And we found that they correspond to 3 different electronic states that can be observed in experiment. But in some sense, O2 is a very difficult molecule. It's one of the most difficult to model. And maybe it was not a good idea to start with O2. But anyway, we already started, so it's done. Okay, let's go further. Now I discuss something what you already know and probably we don't have to discuss. But your book is putting very strong accent on this, so we just discuss for a very short moment. Namely, Lewis structures. Let's start with atoms. To write Lewis structure for atom, you put the symbol of the element and then you put number of dots. In the hydrogen has only 1 valence electron, you put 1 dot. For helium, helium depends on thinking. Helium has either 2 valence electrons, or if you think that helium is a closed shell, the helium has 0 valence electrons. It depends on thinking. I prefer the version with 0 valence electrons. Because valence electrons means electrons that can react easily. Helium doesn't have such electrons. Lithium. Lithium has only 1 valence electron. Next one is beryllium with 2 valence electrons. Then is boron with 3 valence electrons. And now, generally, you have a freedom to put the dots. You can put them all together or separately, doesn't matter. Carbon has 4. Nitrogen has 5. Oxygen has 6. Fluorine has 7. And so on and so on. Now, sometimes, like in the case of nitrogen, I put 2 of them together. In the case of oxygen, I put twice 2 of them together. In the fluorine, 3 of them like that together. Why I did it? Because in most of the cases, nitrogen can have 3 bonds. Oxygen can have 2 bonds. Fluorine can have only 1 bond. Carbon can have 4 bonds. Boron can have 3 bonds. Beryllium only 2 bonds. So this number of unpaired dots usually show us how many bonds a molecule can make. Again, this is usually because there are many exceptions to this rule. Okay. Good. This is for atoms. Now, we said that every molecule wants to be happy. The happy means that it tries to have 0 or 8 valence electrons. So you see that helium atom is already happy. To make hydrogen happy, you have to remove this electron making H+. Now hydrogen is happy. Lithium happy, remove electron. Beryllium happy, remove 2 electrons. With boron we have already a problem because there can be 2 possibilities. One is remove 3 electrons. Another one is add 5 electrons. Turns out that both of them cost very much and none of them never happens. Similar things for carbon. You can imagine carbon 4 plus or carbon 4 minus. Turns out that adding 4 or taking 4 electrons is too expensive. It never happens. Similar thing for the hydrogen. You can imagine N3 minus or N3 plus, 5 plus. Again, too expensive. Now, for oxygen, it's already okay to add 2 electrons, making 2 minus, and this is okay. For fluorine, it's very easy to add 1 electron, making F minus. So now from atoms, we went to ions. This Lewis structure here, they help to understand why you never see ions of carbon, boron, nitrogen. You can see usually the ions that have 1 or 2 plus or minus charge. Because adding 1 or taking 1 or adding 2 or taking 2 is easier than adding 3 or 5, taking 5. Good. These are the Lewis structures for ions. Now we go to molecules. For the molecule, you put the central atom in the middle. You make the Lewis structure for the atom. And now you take other atoms in this molecule, for example hydrogens, and put them around, each of them with 1 dot. So now you made every hydrogen atom happy by having full valence shell of 2 electrons. And at the same time you made the carbon happy, making 8 electrons. In the valence shell. What is the weak point of Lewis structure comparing to the hybridization we discussed a moment ago? Here you don't know the shape of the molecule. It looks flat, but it's not flat. We know that the real molecule looks like that. So to be completely honest with you, last time I was using Lewis structure was when I was at the first grade of the university and I had to pass the exam. I never again used it. Because it's simple, that's true. It helps to understand, but it was invented in 1916. At this time there was no quantum mechanics. People didn't understand orbitals and wave functions. So making such a nice plot and explaining why CH4 is a molecule was already an achievement. But now when we know much more, we know quantum mechanics and orbitals, I think using Lewis structures is still not, it's already not very fashionable first. Second, is not very wise because you make a lot of mistakes. Well, what kind of mistakes? O2, O2. Let's analyze the O2 molecule. One of them has 6 valence electrons. The other one has 6 valence electrons. The only way of making them happy is taking this dot, putting it here, taking this dot and putting it here. So finally when I draw it together, that will look like that. You're probably not familiar with this, but very often in the Lewis structure, instead of writing 2 dots, people are writing 1 stroke. So just replace the 2 dots by strokes. You have double bond in the oxygen molecule. But the real story here is telling that instead of having double bond, you have something else. You have single bond coming. We didn't define the bond yet. Okay, maybe that's a good moment to define a bond. If sigma orbital is doubly occupied and the corresponding sigma antibonding is doubly occupied, bonding is cancelled by antibonding. The positive energy is cancelled by negative energy. So this one has no effect for bonding. This one has no effect for bonding. Here, 2 electrons on the bonding orbital, 0 electrons on the antibonding orbitals. This makes 1 bond. Here, 2 electrons on the bonding orbital, 1 electron on the antibonding orbital. This makes half bond. The reason for this is that the bond order is sum of electrons on bonding orbitals minus the summation of electrons on antibonding orbitals. I write it down. So these are electrons on bonding orbitals, and here are electrons on antibonding orbitals. And to be honest, to get the bond order, you have to divide this one by 1/2. The reason is that bonding orbital has 2 electrons. So the difference in electron must be divided by 1/2 to get the number of bonds. So if we calculated this one here, what we get? 2 bonding, 4 bonding, 6 bonding, 8 bonding, 10 bonding. We get that the bond order is 1/2 of 10 minus 10 because 2 bonding, 4 bonding, 6 bonding, 8 bonding, 10 bonding orbitals, electrons. Now I'm calculating the electrons on antibonding orbitals. 2, 4, 5, 6. Difference is 4 divided by 2 is 2. You may tell me, no, we got the same results. Here there are 2 bonds. Here there are 2 bonds. Almost true. Because you see from this picture that here is 2, 0, 1, real bond. Here is 2-1 half bond. And here is another 2-1 half bond. So this 2 here means 1 plus 0.5 plus 0.5. So the real structure of the OO molecule can be written in the following way. Single bond, half bond, half bond. Not like that, 2 bonds. You tell me, well, what the difference? Writing twice half bonds or writing full bonds? No difference. There is a difference for the specific reason. Single bond tells us that one orbital is fully occupied and the second orbital is fully occupied. It means on one orbital there are 2 electrons, like that, and the other orbital has also 2 electrons, like that. So you see that the spin up and spin down cancel here and here. But in our case, we see that the spin here doesn't cancel. So the molecule has some, with the plus minus cancels, but here is only plus and here is only plus. So the molecule has 2 spins and they can interact with magnetic field. Turns out that oxygen really interacts with magnetic field. If you make a liquid oxygen, you can move it by a magnetic field, which is kind of interesting. If the Lewis structure is true with 2 doubly occupied bonds, then there is 0 spin, no magnetic interaction here possible. But in this case, it is possible. Okay, so that was example that if you go really deep, then the Lewis structures are not working very well. But you don't have to go so deep. Another example for this would be the ozone molecule. Ozone molecule looks like that. Okay. If you try to write Lewis structure for ozone molecule, then you start, of course, with 2 lone pairs, single atom. You put the other oxygen on the side. You have the single unpaired electron. You have single unpaired electrons. You get something like this. But looking at this for a moment, this is not such a nice thing because this one has unpaired electron and this one has unpaired electron. But the real ozone doesn't have unpaired electrons. What to do then? Well, one way of proceeding with this one is doing the following arrangement, saying that this unpaired electron is not on this side, but is on this side. And this unpaired electron can travel all the way here, traveling here, making a molecule that looks like that. I can already understand the triple bond for oxygen. It's okay. But this molecule is not symmetric. Why the experiment shows that the molecule is perfectly symmetric. This bond and this bond is the same. So what the Lewis structure did, he said that there is a resonance. With another molecule like that. And for a long, long time, people were understanding the word resonance. It's written like that. And resonance means that something is vibrating. Okay, so when you have a string and the string is not vibrating, this is quiet string. When the string starts vibrating and it's standing wave, you say that this string is in resonance. So what people said that these two structures are in resonance. And for a long time, there was no very clear understanding what does it mean resonance. So some people were thinking that this molecule is changing very fast into this and changing back, all the time changing. But this is not true. Such changing doesn't happen. Turns out that this molecule always looks like that. This type of resonance structures happen very often. I give you some other examples. Take the molecule NO3 minus. This is anion. Looks like that. Nitrogen in the middle, one oxygen here, one oxygen here, one oxygen here, 120 degrees between them, flat. Now, if this is NO3 minus, we have some problem here, because according to the Lewis structure, the Lewis structure should look like that. Of course, everything has a minus. It means that two single bonds and two double bonds. Again, the experiment shows that this is symmetric. There is no single, there is no double. All bonds are the same. So what people do, they say that there are three forms. And they just transfer into each other. Again, no such transfer was observed in experiment. Nothing like that happens. So it looks like the Lewis structures are just simply wrong, because the real structure of the molecule looks like that. N in the middle, O, O, O. This is single bond. Now, this molecule has one pi bond, and the shape of the pi orbital looks like that. It includes all atoms. It means that this bond is 1/3 here, 1/3 here, and 1/3 here. So the bond order here is 1 and 1/3. The same bond order here and the same bond order here. If we do this, then it's not a problem where to put double bond. There is no double bond there at all. There is one bond that includes all the atoms. So for me, the largest problem that comes from Lewis structures, that Lewis structures always tries to describe the molecule as bonds between two atoms. Two atoms make one bond, another two atoms make another bond, another bond, another bond, and you make everything out of bonds. Turns out it's not true. In this molecule, this half bond is made because in reality, there is a single bond between oxygen and oxygen. There is a single bond between oxygen and oxygen, and there is one pi bond that looks like that. And this pi bond includes three atoms. Then when you divide these one pi bonds into two, then you get 1/2 and 1/2. Similar things happen for oxygen. Here you have only two atoms, so it's more difficult to describe this, but oxygen, oxygen, sigma bond, and now you have pi bond this one. I tried to make the plot. Now, there is also another one. The another one would be here, here and behind. You know that every pi bond has two signs, plus and minus, right? And the another one, this one, I cannot plot here because one would be above the blackboard, another one would be behind the blackboard, another pi bond. Okay, but now we have this, pi antibonding. We know that pi antibonding is changing sign between. It means that the pi antibonding will look something like that. Plus, minus, minus, plus. Now what happens? Plus and minus kind of cancels. And plus of minus cancels. Here, sorry, here would be minus minus. Once again. So we have plus and minus that cancels. Here you have plus and plus that is okay, that making the bond larger. On this side you have minus and plus that cancels, and you have minus and minus that makes the bond larger. So half of the bond is cancelled, only half is surviving. That's why we are making the half bond in these orbital pictures. This is one way of understanding this. This is not very correct mathematically, but that's how you can think how the half bond is made. And another situation like that happens in this plane, here and behind.